it is become now an interdisciplinary area, which involves expertise from many different disciplines. When we go to deploy these technologies in the real-time practical applications. Okay, so we'll touch on these. So, what is the importance of water quality monitoring? So, conventionally, we talk mostly about the prevention and remediation. For example, when you are going to consume water, either for drinking for any other or any other applications, you want to make sure whatever water we are consuming, it is free from contaminants. So we make some attempts or we take some measures to prevent the pollution to happen. And once it has happened, for example, after the industrial treatment, some effluents are released into the environment. We have to make sure that that water is free of the contaminant before it is reused later for some other purpose, either for drinking or for irrigation or any other purpose. Okay. So this is important in context of regulation enforcement because all the pollution control boards want to ensure that whatever water is released in the environment, like rivers and other water bodies, or it is for any other purpose, it should meet some standards. So this requires testing of the water quality to make sure all the parameters are within the threshold limit. Apart from this, there is one more aspect which we don't discuss so often, but it is also of importance, which I will touch upon here. Water security monitoring. This is important because if you see, unlike the other things, our water bodies, whether it is like rivers or oceans, they are open to everyone. It is just not only limited to a particular state or particular country. For example, many rivers will flow across the nations and so on. Similarly, all these are not always protected. So this gives an opportunity for sometimes to unsocial elements to tamper with these water bodies, and that can cause very much harm to the people and society. Okay. I'll just give you a few examples, uh, which is related to pollution, but it touches upon some other aspects also. For example, sometimes apart from the contamination that we already are aware of, resulting from the anthropogenic activities or from industrial, sometimes some unexpected contamination may occur. For example, microbes may become resistant to established treatment procedures. For example, typically, if you see in water treatment techniques, one of the very important steps is treatment with chlorine or something. But sometimes it happens over a period of time. These microbes may become immune or mutated so that they will bypass this treatment procedure. So even though we may be thinking that we have treated the water, but it may not be still usable for various. Other than that, sometimes accidental contamination happen. So I have given some examples. It happened in Scotland in 90s and in Finland when some of the water supplies were accidentally contaminated with different things, with biological or chemical contaminants. And unless you have the measures to make sure that water is being used for different purposes is free from these contaminants, these kinds of things can cause damage to the community health. Other than that, also I pointed out a couple of examples here. It happened in 70s when some of the extremist people they deliberately contaminated the water. So they induced the typhoid containing bacteria in the water supplies in a major city like Chicago, and it became a major threat. Similarly, in 2000 also it happened. Uh, there was some agitation going on by some workers, and they intentionally dumped huge amount of sulfuric acid into the river tube, which can very well go and get mixed with the water supplies, and it can cause damage. So such things are happening, and they cannot be ruled out. So we have to make sure that enough measures are taken that these kind of things can be avoided, and whatever water is consumed is free from these kind of contaminants. Just to, on the lighter side, many of us might have watched some of these movies. So it is said that popular culture like fiction, whether it is in form of movies or dramas or novels and so on, it is not far from reality. Although they may be works of fiction, but they are related to the activities that we are going on right now, or sometimes they may become reality in future. So you might have seen some of the movies like Tuxedo and so on, in that a corporate creates the poisoning of nature water reservoir by means of some GMO modified insects. Or the Batman Begins is even more popular one, where villain attempts to introduce the hallucinogen in water supply. Okay. These are some examples of such kind of fiction work. And if you are interested in reading some novels, there was one novel which talks about some chemical that change the properties such that the water could become frozen at the room temperature. So it becomes unusable for real and effective. Okay. All this I just want to suggest that there is importance of water quality monitoring to make sure that we know what is the water we are consuming is free from different contaminants. Now, historically, if you see water quality monitoring, whatever progress has been made, it is limited to certain aspects. For example, I have shown here some of the typical techniques like AS or other techniques which are used for analysis of water. So most of these require sophisticated techniques, and they involve high costs related to sample collection, because you have to collect the samples at the different locations and then take it to the centralized lab facilities where there these equipments are located and you analyze the water for different characteristics. And there has been, can say, relatively less awareness of the advances in this art. So, but this lot of need has been realized to make further advancement in this area, and many of the regulatory actions which have been taking place in India as well as all over the world, they are making sure that significant stress is given on these aspects so that they can be made, we can say, more awareness can be generated and more sustainable technologies can be developed in this. For example, here in India, there is the TICAP vision which is there for 2035. One of the aspects of it is related to instant potable water quality testing. And similarly, in other countries like EU, European Union Water Directive, it also emphasizes specifically on the monitoring quality of water, which is intended for human. So generally, if we talk about the water quality monitoring, we measure the parameters, the common parameters like turbidity, pH, temperature, and depending on the site which you are testing the water, then you may be interested in specific chemicals like chlorine, particle count, total organic carbon. And if it is industrial water, then you may be also want to know about what kind of contaminants are present. So for all these physical, chemical, or biological aspects, typically we use these kind of techniques that you might have read in your courses like AS or using the conductivity meter, potentiometry, or ion selective electrodes and so on. But if you see, most of these techniques which are described and which we have read in our courses, most of them are they employ sophisticated equipment. They are lab based, and often they require expensive chemicals, which make them quite you can say quite expensive to operate, and also they are labor intensive, time consuming, and most of them employ offline monitoring. That means you have to collect the samples, take it to the testing laboratory, and then test. And when you are dealing with such equipment, they obviously they need maintenance and they also degrade over time. If you think of an ideal world in this particular scenario, they are looking for an ideal sensor which can detect many of these contaminants at the same time overcome some of the challenges which were listed in the previous slide. For example, we want an ideal detection technique which allows acquisition, maintenance, and upgrades at an affordable cost because economics is very important. And it should require low skill and training. So even common people or with the minimum technical knowledge, they should be able to operate it. And we should identify the source at the site of the contaminant. Actually, if you can identify this, whatever is causing the pollution near to the source, you can design your remediation technique to be more effective. Otherwise, if you see everything gets mixed up, if all the effluents are coming from the different sources and they are all mixed up, then it is very difficult to know from where this contamination is coming, and then it becomes difficult to design an appropriate pollution remediation technique. Apart from this, it should allow robust methods of operation, and it should have significant degree of automation so that minimal human intervention is involved, and it should function continuously. So these are all what we require ideally, but it may not be possible for one technique at present to accomplish all these things. But this sets, you can say, a goal towards which we should be working so that we can design such technologies and develop. Now, here specifically, I'm going to talk about one of the techniques which have become very popular over the last 1 or 2 decades. We call it lab-on-chip technology. Some of you might have heard of it. Those of you not, I just introduce that what it means. In fact, it is not entirely new thing. It is a quite popular thing in many of the areas like biomedical, which we have also used in our daily life. And it also has applications in environmental area that I mentioned. So what lab on a chip means, as the name indicates, lab on a chip. That means if you are able to do many of the laboratory functions, many of the analytical functions which you do in a typical chemical or allied laboratories, if you can miniaturize them and do on a small piece of chip, even just like a microscopic slide size or a credit card size, something like that. So we are miniaturizing the entire lab operations on a small scale. That is called lab on a chip. So when we say this, we are talking about the dimensions. For example, if you need to have flows, they will need to be in channels which will be of micron size. And the volumes that will be flowing in this, it will be microliter, nanoliter, even below. And device size will be typically, which you can hold it in your hand, millimeter or centimeters. So just to give you an idea, which something which you are familiar with, you might have seen this diabetes testing instruments, right? How they work. Do any of you know how it works? I have just given a, I can say, a breakup of the different components of a typical strip or in the instrument, or how it works. You have different layers, and these layers are such that if you know how it works, if we take a small, very tiny droplet of blood, we have this small needle which comes along with the equipment. You pick it on your finger, small droplet of blood will come out. There will be a strip there, or you can say an entry point where you will put this drop. Since that it is made up of actually a microchannel, we know that in the microchannels, capillary action will take place. Okay. So as soon as you put the blood drop, it will automatically flow inside. So this is what designed for that. And inside that, what happens is there is an enzymatic reaction takes place. It's kind of an electrochemical reaction. For each molecule of glucose which interacts there, you can say roughly some particular number of electrons are released. Let us say 2 electrons are released per glucose molecule. So what we have done is we have tried to relate how much amount of glucose is present in the blood to the amount of electrons which are released in this electrochemical reaction. On those, there is an electronic circuit there which will measure how many electrons are released and will give you an output in form of a number which is calibrated. So it is relating how much of glucose is present to what is coming out in form of electronic signal and in form of a digital signal. So you are able to measure what is the content of glucose present in your blood and whether it is high or low, that you know accordingly. So this is what is happening. So we have done entire thing on a very small scale of you can say a lab on a chip. That is what it is. Okay. So these type of things have become commercialized, especially in the biomedical area a lot. Many other test strips also are coming, like pregnancy test strip or the diabetes test strip, and many other drug testing test strips. And same concept can be applied for other applications, including the water quality monitoring and even food quality testing and so on. Okay. So that is what I just want to illustrate here. Now, if you see why it has become so attractive to develop and design these things. Okay. So I've given some of the advantages. There is a huge reduction in volumes when you go from the large scale to the small scale. If you operate any of these experiments on the large scale, you will be working with, let us say, milliliters or even larger volumes. Here we are going to deal with microliters or nanoliters. So as soon as you reduce the volume requirement, your cost will come down. And if you are dealing with any expensive reagents, you're saving cost there. And when any reaction is happening, some byproducts will also be generated. So if the quantities of reactants are less, products also, byproducts, everything will be less. So we are reducing the waste generation. If you're working with a small scale, you have less fabrication cost. And then analysis is much faster. Here I talk about some chemical engineering aspects which you relate to. And you allow high screening. And these devices can be very easily designed and modified because it's such a small scale of things. Cost of fabrication, cost of development, everything is reduced. Now here we talk about what something which we are familiar as we study in our courses. When we talk about the small scales, we have much higher heat and mass transfer rate because if you see dt by dx, if you see delta x is very small. If you are able to accomplish the delta t in a very small distance, you're talking about very efficient mass transfer and heat transfer and so on. And we have short residence time, so if you're doing any of the reactions, and we have less dispersion. And there is a very important role of fluid surface to volume ratio. That's why this micro and nano things are very important, become very popular, because you are able to achieve much higher surface area in a very limited amount of volume. And one of the things that comes into picture, that is called when we flow in these channels, we have laminar flows. For example, if you can see this, what is happening is we have this wide shape of entry. So two fluids are coming next to each other. But if you do the same thing in the macro scale, you'll have immediate spontaneous mixing, right? But in the micro scale, because this in the laminar flow happens, there is a very limited mixing at the interface. Only mixing which occurs is because of diffusion. Okay, so you're able to achieve much controlled flows with well-defined interface, which is not possible on the macro scale. Okay, so apart from the volume requirements, cost things, there are some technical advantages also that come into play. Okay, so just an illustration of when you go to the lower scale, how we can achieve much higher surface area to volume ratio. So we have this helps us to achieve higher heat and mass transfer rate and more reaction. Okay, so I've given some examples from literature which have been reported and they are also being commercialized, especially with respect to water quality monitoring. So if you can see in this one here, you can collect the samples directly from the site, for example, any contaminated water site or any natural water body. And there is a entry point here, in which it is made up of several micro scale channels. Once you put this sample of, you can say, a water droplet there, it will flow into different micro channels. And each of the micro channels will have some specific reaction that can take place, which helps us to detect the contaminant. Now, how these contaminants are detected, just to illustrate that there are many types of detection approaches that are typically followed for different types of applications. You can have signals in form of colorimetric, which allows us to see the color change. For example, if you remember your chemistry experiments, we used to see how the color changes and helps to detect particular type of metal or any other contaminant. So there's that technique. Or if you want some more, you can say more precise signals, people also go for electrochemical or photoelectrochemical signals. It depends on the type of analyte you're interested in and how much is precision you want. I'll give some examples on it just to illustrate it here. This is based on fluorescence signal. Okay, so they were trying to monitor the amount of carbon dioxide which is present in the water which was collected from sewers and wells. So they did a particular type of reaction such that depending on the concentration, you'll have different amount of fluorescent signals generated. Okay, so if you just take an image of this fluorescent image, you'll be able to tell how much of amount of carbon dioxide is present. Okay. Similarly, if you are doing the electrochemical ones, then they rely instead of the color, they rely on the base of electrical signal. Either it can form the current or voltage, and so on, depending on the type of the device is there. Okay, so that is about this. But if you see, even these micro channels which you have to make, it is not always easy to fabricate. In you can say in a common lab scenarios like that we have in our different institutes. So we are looking for something which can be made even more sustainable. So that has led to the development of some alternative techniques of fabrication and device development. So these are based on as simple thing as paper. Okay, the same paper that we use in our labs, like filter paper. We can design such devices even using a common filter paper. So I'll just give you some examples of that. Okay. For example, if you see here, this is actually the device which was developed by some scientists. They have taken a simple piece of filter paper and they have defined very specific areas in which they are doing some reaction, which is helping them to analyze certain contaminant. Depending on the concentration of the contaminant, you will get different color signals. Okay, so this is very, you can say this device can be made within even 10 rupees or even lesser, depending on the cost of the reagent. Okay, so I'll just illustrate how these are fabricated and then some examples. And there is actually a startup in India itself. This is the company in Bangalore, Akira Labs. They are actually working on commercializing these aspects, and they have gone even beyond paper. They are using some textiles, based materials, to develop some of these kits. For example, the one here, it is shown. I think it is some kind of again a biomedical kit there. The advantage of using the cloth or textile instead of paper is it has the same properties of paper. See, why paper has become very attractive is because if you don't need any pumping or anything, it is automatically made up of this cellulosic material or cellulosic matrix. So if you put any liquid sample or reagent on it, it will spontaneously flow by capillary reaction. You don't need any pumping. So if you design a device like this is actually made up of cloth. So cloth also is made up of cellulose. So it will also have same properties. And at the other end is it is also flexible and robust, unlike paper. So they are using it for commercial. So now I just discuss about how it can be very easily fabricated. Okay. For example, suppose I have this filter paper. Okay. This filter paper is made up of this cellulosic matrix. Okay. If I put a drop of any liquid, even just say water, what will happen if you put a drop of this on filter paper? It will spread everywhere by capillary reaction. It will spread in a radial direction uniformly because there is no constraint anywhere. Suppose I want to confine the flow or confine the region in which I want this liquid to spread, something like this. So what I need to do is want to keep this center area as hydrophilic. Rest of the things I want to keep it hydrophobic. If it is hydrophobic, no water or water-like liquid can flow out of this area. So what they do is very simple technique is you can coat with something like wax. If you take a wax candle or a wax crayon, and if you just draw a circle boundary like this, okay. Now you have taken a circle and just a crayon like this and drawn it. It is in form of a solid wax. Now if you take this piece of paper, which has a circular drawing in form of a wax circle, put it on a hot plate or in an oven. What will happen is this wax will melt. And once it melts, it will permeate through the cellulosic matrix, which is paper is porous. Once wax converts from solid to liquid, it will permeate inside. So it has gone inside the paper. Now you remove this paper from the hot plate or oven. What will happen again it will become solid. But now what has happened, it has permeated through the matrix of the paper. So once it becomes solid again, it has formed a hydrophobic boundary. So eventually what happens is you have formed a hydrophobic boundary like this. I have the center area which is hydrophilic and I have the boundary which is hydrophobic. Now this has become, I can say, a reaction zone. If I want to do any reaction, it will be confined only to this. If I put a reagent, suppose I want to detect chromium, there is a reaction which says that chromium reacts with DPC, diphenyl carbazide, and will give me a complex which is of purple color. So what I do is I'll put my DPC only in this region. Since it is a very small circle, I'll need only one, let us say 2 microliters, okay, for this particular diameter. So I'll coat it with DPC. Now I take this unknown sample from anywhere. Suppose I take it from any river, one sample. I put that water sample here. If it has chromium present, it will react with DPC and will give me a complex which will be of purple color. If there is no chromium present, it will not give any color. So I'll say that no chromium is present. Okay. Now suppose I design many circles like this and coat all of them with DPC. Okay. Now depending on the concentration of chromium, if my concentration of chromium is less, I'll get a particular color. If my concentration of chromium is more, I get a more intense color. If my concentration is even more, I'll get a further intensity of color. So I can relate how this concentration is relating to intensity of color. Okay. Now this, if you see any color, it is made up of actually 3 elements R, G, and B, red, green, and blue. Okay. So I can define an intensity which is related to concentration, and I can generate a calibration chart, intensity versus concentration. Suppose I get something like this. So it allows me to do a quantitative measurement also apart from qualitative measurement. So if I take any unknown sample and if I'm able to measure the color, I can back calculate it to find out the corresponding concentration. So it is not only qualitative method, but also it allows me to quantitative method. So here I have shown some examples from the literature. For example, here this actually they made it visually, instead of doing the circle, they made this design in form of a symbol of chromium to make it just visually appealing. So that if chromium is present, it will appear in form of a purple color. This was a very simple example. Here you can extend it to different designs because it is very easy to do in the paper. So they made a design like this. In this, they made a multiple test zones. In this, what happens is once you put the sample here, so this is all hydrophilic region, and outside this design is hydrophobic region. Once I introduce the sample here, if I put at a certain amount of volume of liquid, it will flow by capillary action in all these different regions. And here they have done the multiple analytical testing. For example, they have done for copper, mercury, chromium, and nickel. So, like I gave an example of reaction, chromium plus BPC gives me purple color. Similarly, there is an for copper, let us say, copper reacts with some other reagent, it gives me a different color. So, what they did is they coated different areas which were called as reduction zones with different reagents. One was specific for copper, one for chromium, one for Hg, and so on. So depending on whether the analyte was present or not, accordingly you will get a color change. Okay, so this was the approach that was used. Now these things can be very easily designed, and you can make any type of designs for your own application. For example, here in this case, uh, they made this type of design in which you introduce a sample in the center. Sample flow in a different ways by capillary action. Here they introduce by this way, where it flows by from this and goes into a different. So these things are very easy to design and fabricate depending on the requirement. That's why they are becoming very, can say, very promising alternatives for portable testing. Okay, so this is something what I explained just now. Actually, the whole field of this fabrication has actually been inspired from semiconductor industry. Uh, uh, in semiconductors, there are techniques called as photolithographic techniques, which are based on this kind of a selective patterning. Here also we are doing this called as patterning. We are making different patterns in which one of the regions has certain properties, other region has other properties. So this is coming from the electronics industry, in which they make these chips, the ones that we use in our mobiles and computers and so on. They have to make these chips, large amount of transistors and everything on a very small silicon chip. They make use of this photographic technique. This has this entire thing is inspired from there, but it has become, we can say, more sustainable from point of view because it is very cheaper and can be done with very easy things. If you do in the electronics industry, you have to work with the clean rooms, they call it. Clean rooms are, you can say, a room like this. Clean rooms are defined as, uh, suppose if I take any air sample here, it will have a lot of dust particles and so on. Clean rooms are designed such that air will be very, very pure. There will be very less count of the dust particles. So that is defined in terms of how much amount of dust particles or particles are present in each unit volume of air. Because you're working with these chips, you need very precise dimensions. If any of the dust particle goes there, entire chips is destroyed. But unlike those things, these things can be done in a very, can say, simpler methods for our application. Okay, so there are some more examples. Also, this they have done it for nitrite contamination. So different. This is called as spot test, the one we defined just now, and these are called as flow test. Okay, where you introduce a sample, it flows into different channels, and these are the spots. Okay, so not only this chemical contaminants, but you can use it for different other applications like biological contaminants also. People are doing this live bacterial assays on this, in which you can, with time, you can monitor how the bacteria is growing or changing its properties and so on. Now, these can be made more and more sophisticated depending on the requirements and depending on the resources we have. For example, you might have seen these kind of things where you can reduce some kind of add-ons to your mobile. Okay. So this will allow us to detect very precise root analysis on the mobile itself. Okay, so with the advantages of the smartphone imaging, now these have become even more portable. For example, once you do this kind of a reaction, you don't need anything apart from mobile camera to analyze it, because you can take the picture of your the colorimetric reaction using your own mobile camera, and you will get depending on different concentrations, you will get colors of different densities, which you can, if there is not even the apps are available, or this app can be designed also, which can help us to generate this kind of intensity versus concentration calibration from this. So instantly you can measure it and you can know whether contaminant is present or not, as well as how much it is present. Okay, so this is an example in which what they did was they designed this method like this, and they also designed an app. Okay, and with the help of that, they were able to quantify within the using the simple mobile what was the contaminant present and how much of the concentration of each contaminant. Okay, so just to illustrate, depending on the resources which we have available and depending on the type of contaminant we want to detect, we can make them very as simple as this, where you just need a dropper of pipette to introduce the sample, just a piece of paper in which you can design this whole thing, and you can test with your mobile. If you have more resources, you can design it more precisely, and you can also make more sophisticated things in which you can design these strips, like in the case of glucometer, which happens. So depending on the type of the things you are interested in, you can design these type of things. Both come under the purview of lab on chip techniques. Nevertheless, there are challenges because this is actually a very developing field. So, and it has to do benchmarking with established techniques. We cannot expect that right at that moment it will match what is happening in the calculations you are getting from the AAS. You can try to recollect when COVID was happening. What was the standard benchmark technique was used? It was PCR test. But people were trying to develop some alternative techniques like rapid antigen kits, all one. They had some accuracy, but not always on the benchmark of the PCR technique. So that was you can say the rapid antigen kit which was being developed, that was under the purview of lab on chip. It was based on the same concept. So they are the challenges which I have summarized till now. They are in terms of material stability, energy supply, filtration, production cost, and so on. For example, you want to work with the materials which are stable, because typically when we work with the labs, we have very sturdy things and so on. But if you're working with the paper, there are limitations which people are trying to overcome by using some alternative polymers or even cloth and other textile materials, developing smart polymers for that. And then is the stability of the reactants involved. See, when you are coating these things, for example, if you take any of these strips and you let us say you want to do enzymatic reaction, okay, on these enzymatic, you coat it with the enzyme, it will have a particular shelf life, beyond which you cannot do that. You cannot use it reliably. So these type of things are there still, which have to be overcome. So you need to design some biomolecules which are more stable, and so that shelf life can be extended for longer purpose, especially if you are doing the bio-based reaction. Then if you are working with the capillary reactions, we don't need any external pumping. But sometimes it may not always be possible that we are able to manage the capillary reaction. Then in that case, we need to have the flows. Then there are some syringe pumps or micro scale pumps which are available to drive the flows. Then energy aspects will come in. Then one of the important aspects is to make sure that there is no interference. Because when we are talking about the real sample testing, even water, it's not that only chromium contamination is there if I take a water sample from Ganga River. There may be many other things which also may be present. Sometimes it may be possible that those contaminants may interfere with this reaction, PR plus DPC. Suppose something else also reacts with DPC, then I may get a false signal. So I have to make sure that interference is not there, or if it is there, I have to do some kind of a blocking to prevent it. So these aspects must be taken into account before these things are taken into the commercial application. Okay, and then anything which you want to commercialize, it should be also sustainable from the point of view of large scale throughput and production. Okay, so since this is a developing technique, when we go before we go for the commercial scale, there have to be proper methods for high scale production, supply chain, and okay. So always, as I said, there will be compromise between the type of applications or type of features you can have on a device and sophistication. If you want more features on a single device, it will automatically increase the cost. If you want it to be, suppose a small device you make, if you want to be automated, then obviously it will increase the cost. So depending on what our requirements are, what our target application is, we have to design the thing. Suppose you want to devise something just to test the contamination of chromium in a remote area like a mountainous area or in a particular setting, rural setting, you will design a cheaper device. Suppose you want to design a device for some industrial effluent, you can afford to have more sophisticated design. Depending on the application you are targeting, you can have such kind of a design. And just to illustrate this related to our wastewater treatment, which we are most often involved in as chemical engineers. wastewater epidemiology is one of the methods which you can say came into it got more awareness during the time of the COVID. In this case, what they do is they collected water samples from, let us say, a community. For example, you are living in a residential area. They'll collect the water samples from that area and they will try to analyze it for some kind of contaminants. Typically, it is done for biological contaminants like viruses and so on. And based on the inference you get from there, they try to relate to the community health. So this technique was gained quite prominence in during the time of COVID and was used for such things. So they took the samples of feces and urine from disease carriers and tried to get if COVID was there. So what it tells us, in future we can envision that we can have the integrated systems where we'll have the water quality monitoring tools combined with the water treatment things. So you can have in a single kind of a facility, you can test and you can make some inferences which are useful for further application. Okay, now if you see this lab on chip techniques, as I was trying to tell in the earlier slides, this technique involves input from many disciplines. It's not only a chemist or a chemical engineer. When you are going to design these devices, if you want to then automate them, if you want to do some kind of image analysis on the image processing, you need people from different backgrounds. They will come together and design this device. So, in fact, most of the cutting edge technologies which are being developed in different fields, they are involving actually multidisciplines. So, there's an approach, there's an opportunity for all of us to look into these directions. So in future, we envision that we will have such devices which will allow us for on-site estimation and real-time detection. Okay, so and these devices should also be made more, you can say, user-friendly. For example, if you have this outputs like this, which can be color-coded, even people who are illiterate, they will be able to see whether water is contaminated or not if they just look at the color. So there is a need to develop these devices which can be used for large amount of population, whether illiterate or literate, educated or uneducated. Okay, so in our lab also we are working on some of these things and we have developed these devices for detection of some heavy metals or even food contaminants. And this type of things, we are also trying to illustrate simple concepts like we study in our courses like continuity equation or laminar flows. We can make such type of designs to illustrate these principles without needing any of the sophisticated. Okay, so in future we expect that these type of techniques will allow us to develop affordable and accessible point of view sensor, something we can take it to the point of testing and use it there. Instead of taking the samples and bringing to the lab, I am taking my lab to the site and testing it there. So, and eventually it will help us to integrate different aspects like water quality monitoring, water treatment, and even healthcare aspects to develop a integrated solutions for all. So that's all I have. Thank you all for your patience. If you have any questions now or later, you can answer. See, if you're using the paper, something like that, it is one-time use access. Okay. But there are ways, if you are using, let us say, cloth, it is possible that if you want to reuse it, you can do something to remove the chemicals which are coated and reuse them. But paper is something so cheap, we design it as disposable. Yeah, you need to use the corresponding chemical to. Yeah.
Thank you for the session, sir. It was great to see so many methods that can be sustainably used for water purification. And we personally love the portion of where sir connected these things in fiction movies because we see those movie, enjoy those movie, and discuss those things with his friends, but we don't do so much focus on the special part that is on water purification. As a chemical engineer, we should obviously go to the motive of the movie. So thank you so much, sir, for introducing such important topics for us. Our next session is Dr. Sandeep Parmatan. He's from IT Kanpur. He'll be coming soon, so let us wait for the next. Just 5 minutes. The next session.
कौन सा है हमें